Hey guys, what we've covered so far, we've talked about forces. So what do forces do? As you can see, this is split into two parts. The top part is covering motion, the bottom part is covering the shape of the object. So you can see for the motion, force, if I apply a force, I can actually cause a rocket to actually slow down, or if I apply it again, you can see it will start to move faster. So basically, it will start to accelerate, decelerate, and this one here, you can see it starts to change direction. You can see it starts to go up over here. Okay, all right. All right, so just to summarize all that into a table, if we have a force, if we apply a force to an object, we can actually cause the object to see two things, okay, to accelerate or decelerate, like what we saw in the animation earlier. Okay, so put that in the table. What it means to accelerate, accelerate means to have a stationary object to either start moving, or a moving object to decelerate will increase the speed. So both of these will be accelerating. And to decelerate, it means to have a moving object to decrease its speed or even to change its direction. So all these are cases of acceleration or deceleration. So you will see, if you apply a force, you will see acceleration or deceleration, right? Okay, so the question to ponder right now is, what if I don't have? What's the opposite of all these? Opposite of acceleration or deceleration will be zero acceleration. So if I have zero acceleration, what can you say about the force? Does it mean there's zero force also? Okay, to answer that, let's look at what we mean by zero acceleration first. Okay, so from definition of acceleration, we know this is a formula: a equals v minus u over t. We substitute a to be zero. You bring t over, 0 equals v minus u, and boom, what do you see here? Zero acceleration. From our definition, we know it means constant velocity, right? So constant velocity, zero acceleration can mean an object can either be moving or not moving. Basically, it's a constant velocity. So if it's not moving, the velocity obviously is zero. If it's moving, it can be any number, okay? So this does not mean, in the case where zero acceleration, doesn't mean that there are no forces, but it means, boom, it means the resultant or net force is zero. Okay, so how we study this is that we're going to go straight into Newton's laws. This forms the basis of Newton's laws of motion. Okay, all right, so let's straight into Newton's first law. Okay, in Newton's first law, you can see that it's all talking about zero acceleration, like what we've been discussing so far. Okay, so zero acceleration, there are two cases here. It's either not moving, or the apple, an object, is moving at constant velocity of 2 meters per second. Both the cases you can see here. Does that mean that there are zero forces? No, there are forces acting. You can see that there are forces, just that the forces are balanced. Okay, they cancel each other out. It means that the zero resultant force acting in both cases. Okay, so when the zero resultant force, Newton's first law states that if an object is at rest, it will remain at rest. If it's in motion in constant velocity, it will keep moving all the way. Okay, so that's Newton's first law. All right, so let's go straight into Newton's second law. Second law, what will happen to, we got three objects here, same masses, but different forces. You can consider this to be resultant forces. So which one do you think will actually accelerate the fastest? Okay, fastest, you can see the one with the largest resultant force, right? Okay, so the bigger the force, the greater the acceleration. All right, what about if I fix the force, the resultant forces, and I vary the mass? Can you guess which one will accelerate the fastest right now? Okay, boom. All right, you can see the 1 kilogram mass, the smallest mass will accelerate the fastest. Okay, so what does all this mean? Okay, if I have a relationship between acceleration, force, and mass, you can see the higher the resultant force on an object, the higher the acceleration. Makes sense, right? Just was in the first animation over there. Okay. Then the second animation, the heavier the mass. What can you say about the acceleration? Acceleration is lower, right? Okay, so this brings us to Newton's second law. If I were to rearrange this relationship, I will get this formula. Force equals mass times acceleration. I'm quite sure you've probably heard this before. This is one of the most popular physics formulas. Just to take note, this force is not just any force. It must be the resultant force. Okay? Okay, so now we are down to the third law, the final law of Newton, Newton's third law. I'm sure you've heard this before, but basically it's when an object exerts a force on a second object, the second object exerts an equal and opposite force on the first. Forces always occurs in pairs. So what does this? I believe you've probably heard this saying that for every action, there's an equal and opposite reaction. Okay, what does this mean? Okay, you can see if I were to push my finger against a pin, there are two forces. There are two bodies here. What are the two bodies? The finger and the pin. And you can see that there are two forces here. What do you notice about both the forces? Yes, they are always the same size and they are acting on different bodies. So you can see equal forces and they are opposite to each other. Okay, one force is acting on the finger, the other one is acting on the pin. Okay, and so you basically, as you can see, the second object exerts an equal and opposite force on the first. So these two forces will always occur in pairs. Okay, so here I've got two of my brothers here. They are on a skating rink, and my brother Blue is going to push brother Red. Okay, so check what happens when he pushes brother Red. Okay, as you can see in Newton's third law, if he were to push brother Red, brother Red will exert, although brother Red gets a force, feels a force from Blue, but brother Blue will also feel a force from red because this is due to Newton's third law. There's an equal and opposite reaction, right? Okay, so just to combine that up into another one, okay, you can see my brother Red has eaten some prata and he's gained a little bit of tummy here. So since he has got more mass right now, okay, when brother Blue pushes brother Red, both of them will have the same equal and opposite forces, right? All right. But if we were to use Newton's second law, that the F of F equals ma, for the same amount of force, if you have a larger mass, what do you think will happen? Which one will accelerate more? Let's check it out. Yeah, brother Blue will accelerate much more than brother Red. Okay? All right, that's because he has got a larger mass, and since he has a larger mass, A equals F over m. M is in the denominator, so the A acceleration for brother A would be less. All right, so let's just summarize what we've covered so far in today's video. We've talked about Newton's first law and second law. Basically, Newton's first law, forces are balanced. It doesn't mean there's no forces. It means that all the forces cancel out, or resultant force is zero. Okay, so in this case, acceleration is also zero, and an object will either remain at rest or continue moving at constant velocity. Okay. Second law, Newton's second law will be the opposite. When resultant force is not zero, that means there is an acceleration. You can either accelerate or decelerate, and it means that it will either start moving or velocity will change or it will stop moving. Okay. So in Newton's second law, actually both of these laws is governed by this formula. Okay, F equals mass times acceleration, where F is not just force, but is your resultant force. Okay, hope you enjoyed this video. See you in the next.